Okay, so in this video, we want to consider the topic of bases and orthogonality. And remember that orthogonal simply means perpendicular. Before we look at the idea of orthogonality, let's consider a very fundamental property of a basis. And recall that bases is simply the plural of basis. So let B be a set, say, of M vectors. So V1, V2, 2Vm. So let B be a basis of the vectors of the space of vectors, say V. So we have a space of vectors. It could be Rn, it could be a line, it could be a plane, or another object, as we saw, say, the kernel of a matrix or the image of a matrix. So V is some space of vectors, and B is a basis of this space. Here's the property of the basis. Every vector in V, can be expressed uniquely as a linear combination of these basis vectors. So every vector in the space of vectors V can be expressed, and the key word here is uniquely, as a linear combination of the basis vectors V1, V2 through Vm. And this is a fundamental property of a basis. So take any vector in V, you can express this vector as a linear combination of the m basis vectors, and not only that, but that linear combination is unique. So there is only one way to express a vector in V as a linear combination of the m basis vectors. Let's prove this, and the proof is actually very easy. There is, though, as you'll see when we get there, there is a fundamental idea, and that is, how do we prove uniqueness of something? So recall that because B is a basis, B must satisfy two key properties. First, property A, the span of B, so the span of these m vectors must be the entire space of vectors V. Property B, because B is a basis, the vectors it contains must be linearly independent. So V1, V2, up to Vm are linearly independent. And with these two properties, you'll see that we will prove this result in just a few lines. So first, property A implies what? Or let me start by picking an arbitrary vector in V. So let U be some vector, any vector that you want in V, in the space of vectors. Well, because B is a basis, the span of B is the entire space, but the span of B is simply the set of all linear combinations of the m vectors V1 to Vm. So that means that any given vector in V must be expressible as a linear combination of these m vectors. So property A implies that there exist real numbers C1, C2, up to Cm, such that, well, every vector in V is a linear combination of these m vectors. Since U is a vector in V, U must be some linear combination of these m vectors, and assume that these are the coefficients. So the vector U will be some linear combination of the m basis vectors. Okay, so that's the first part. We have shown that any vector in the space of vectors U can be expressed as a linear combination of the m basis vectors because the span of B is equal to the entire space. The only thing missing from our proof is the uniqueness of the proof, that there is only one way of expressing U as a linear combination of as a linear combination of V1, V2 up to Vm. So C1 must be unique, same for C2 up to Cm. Well, how do we show uniqueness? Well, the idea is, when you want to prove something is unique, assume you have two of them, and then show that they have to be equal. So assume that we have now another linear combination of these m vectors given the vector u. So assume now that there exists another linear combination, say another set of real numbers, call them A. So A1, A2, up to Am, and these are real numbers. So assume that there exists another set of m real numbers such that U is now this possibly different, who knows, linear combination of the basis vectors. Well, we want to prove uniqueness, so we're saying, oh, okay, well, here's one way to express U as a linear combination of the vectors v1 to vm, and here's another possible way of expressing U as a linear combination of the vectors v1 to vm. We want to show that they have to be the same linear combination. Therefore, we want to show that C1 equals A1, C2 equals A2 up to Cm equals Am, and this will prove uniqueness. That's what we want to show. And this will conclude our proof. Well, how do we prove this? Well, we'll have to use, obviously, property B, the fact that the vectors v1 through vm are linearly independent. And if you remember that the definition, vectors are linearly independent, if the only way to get to the zero vector with a linear combination of these vectors is by the trivial solution, therefore every coefficient must be equal to 0. So we'd like to build a zero vector from these two combinations. Let's just subtract them. U equals this vector, but U also equals this vector. So if we do this minus this, we will get U minus U, which is the zero vector. And now when we subtract both of these together, we'll pair up the two v1s together, the two v2s, and so forth together. And let's see what comes out of this. If you do C1 v1 minus A1 v1, this will give you C1 minus A1 times v1 plus C2 v2 minus A2 v2, so C2 minus A2 v2, up to, finally, CMVM minus AMVM. This will give you CM minus AM times VM. And of course, this is simply U minus U. Therefore, this is the zero vector. And now here's where the property of the vectors being linearly independent kicks in. We have here a linear combination of the vectors v1, right? Some multiple of v1 plus some multiple of v2 up to some multiple of vm being the zero vector. But by assumption, the vectors are linearly independent, which says that the only way to obtain the zero vector with a linear combination of the given vectors is with the trivial solution. And that is the only solution. So B implies that this must be 0. This must be 0 up to this must also be 0. Every coefficient in the linear combination giving the zero vector must be equal to 0 because by assumption the only solution to this equality is the trivial solution. Therefore every coefficient must be equal to 0. But now we're done, because obviously if C1 minus A1 equals 0, C1 is equal to A1. If C2 minus A2 is 0, C2 equals A2, up to finally Cm minus Am equals 0. So obviously Cm is equal to Am, which proves that you have uniqueness. Right? We've said if you were able to express U as a linear combination of the vectors v1 through vm, if I say find a combination of U using v1 up to vm, my coefficients must be the same as yours. So that proves that there is only one way to express U as a combination of the m basis vectors. And this concludes our proof. So very simple but very important property of a basis. Because the basis is a set of generators, the span of the basis is the whole space, every vector in V is a linear combination of the vectors in M. And because the vectors in a basis are linearly independent, this combination is unique. Let's ask now, and this will bring us to the notion of orthogonality, if you had an explicit basis of a vector space, of a space of vectors, so v1, v2 through vm, and you were given some vector in V, how would you find the linear combination? How would you solve for the m coefficients? Well, remember that asking for some multiple of v1 plus some multiple of v2 up to some multiple of vm being equal to the given vector u. So you have the basis vectors, you know all of these m vectors, you know u, and you're trying to solve for the coefficients c1 through cm. Remember that this is equivalent to solving for the variable c1 through cm in the following linear system. The constant terms are the entries of vector u, and the matrix of coefficients is built from one column at a time, the ith column being the ith vector. This is column v1, column v2, up to column vm. So this is something we've done before many times. Whenever you want to express a vector as a linear combination of other vectors, in our case basis vectors, to solve for the coefficients, you just have to solve for the linear system. Now the question is, are there special bases that would allow us to solve for the coefficients in a linear combination without having to solve this linear system? And the answer is yes, and those bases are orthogonal bases. Let's define what an orthogonal basis is, and then we'll show that if we ever have such a basis, and we want to express any vector in our space as a linear combination of these m basis vectors, we will not have to solve the linear system, and there will be a really nice shortcut that will give us the coefficients with the help of the dot product. So, as before, we'll use the same notation. V was our space of vectors, and B, the set of vectors v1 through vm, is a basis of the space of vectors V. And we say that, this is our definition, we say that B, the set of these m vectors, is an orthogonal basis of V if, well, clearly, if B is a basis of V, but the word orthogonal means perpendicular, so if every vector in here is perpendicular to the other vectors, so V1 is orthogonal to V2 up to Vm, V2 is perpendicular to V1, V3 up to Vm, and so on. So if every vector in the basis is perpendicular to every other vector in the basis. So how do we say this very concisely? Well, if the vector Vi is perpendicular to the vector Vj, for, well, a vector cannot be perpendicular to itself unless it's the zero vector, and because we have a basis, the vectors are not the zero vectors. So if we take two distinct vectors in here, whichever they are, v2 with v3, v2 with v7, v8 with v9, v1 with v10, they will always be perpendicular to each other. Therefore, vi is orthogonal to vj for I and j being different. And this usually is said to, you can say this as the vectors are pairwise orthogonal. So any choice of two distinct vectors is perpendicular to each other. That is an orthogonal basis. So every vector in the basis is orthogonal to every other vector in the basis. One other definition, this one very simple. So we say that B, same as before, is, and I will replace orthogonal by orthonormal, if, well, not only are the vectors perpendicular to each other, so the vectors in the basis are pairwise orthogonal, but there is something more. So the vectors are pairwise orthogonal, they're all perpendicular to each other, and on top of this, they all are unit vectors. So the length of every vector in the basis is equal to 1. And that is an orthonormal basis. So orthogonal is simply the vectors are all perpendicular to each other, but the length of v1 could be 17, the length of v2 could be 1/3, and so on. Orthonormal is the vectors are perpendicular to each other, and on top of that, they are all unit vectors. The length of each basis vector is equal to 1. Let's make one simple remark. What if you had an orthogonal basis? How hard would it be to transform this basis into an orthonormal basis? And the answer is not very hard. So if the basis v1, v2 up to Vm is an orthogonal basis, then, well, think of it. Orthonormal is just orthogonal with unit vectors. Well, how can you guarantee that the vectors will keep their direction, but will now be of length 1? If you remember, all you have to do is multiply a vector by 1 over its norm, and the vector becomes a vector with the same direction, but whose length is 1. So then, let's normalize each vector. So 1 over the norm of v1 times vector v1 is now a vector in the direction of v1 whose length is 1. 1 over norm of v2 times vector v2, same thing, up to 1 over the norm of vm times the vector vm. So each vector has kept its direction because we have multiplied each vector by a positive scalar. But because the scalar is 1 over the norm of the vector, each vector has length 1. So then this is now an orthonormal basis. So once you have an orthogonal basis, very easy to get an orthonormal basis. Multiply each vector by 1 over its norm, and you have an orthonormal basis. Okay, so now the question is, if we have an orthogonal basis, and we want to express a vector u as a linear combination of these m basis vectors, how can we avoid having to solve the linear system? And this will be a little theorem, and the proof I will leave up to you. The proof is really short. It takes about 2 or 3 lines. So here's the theorem. So and we'll do it for an orthogonal basis. You can simplify the result if you have an orthonormal basis. But let B be an orthogonal basis of the vector space V. So we have a space of vectors. Suppose we have an orthogonal basis of V. Let U be any vector in V in that space of vectors. So if you express U as a linear combination of these m basis vectors, so some multiple of V1 plus some multiple of V2 up to some multiple of Vm, and you now ask, you say, okay, I know these m basis vectors, I know the vector u, I am trying to solve for the coefficients in this equation. Remember that if you have any given basis, solving for the coefficients c1, c2 through cm in this linear combination will amount to solving this linear system. But if the vectors are long, if you are saying R10, you'll have quite a large linear system. So this will sometimes be quite a lot of work. But now, what we'll show is that if you have an orthogonal basis, you can skip this system and do much simpler. And here's the result. When you express U as a combination of the orthogonal basis vectors, and you want to solve for the coefficients of the linear combination, you do not have to solve the linear system. Here's the shortcut. The ith coefficient for any I will simply be the dot product between U and the ith vector, so this is ci times vi, so the dot product between u and vi divided by vi dotted with itself. And this is true for I being equal to 1, 2, 3, all the way up to m. And that's it. That's the result. If you have an orthogonal basis and you want to express the vector u as a linear combination of the m basis vectors, therefore you're trying to solve for c1, c2 through cm, you do not have to solve the corresponding linear system because the ith coefficient is simply u dotted with vi over vi dotted with vi for any coefficient. So c1 would be u dot v1 over v1 dot v1, c2 u dot v2 over v2 dot v2 up to cm u dot vm over vm dotted with vm. And that's it. Much more efficient than solving for the linear system. And you can look at this result and you'll see that Ci is even simpler if the basis is orthonormal. If it is orthonormal, every vector has length 1, but if you dot a vector with itself, that is the norm of the vector squared. But since the norm of each vector is 1, 1 squared is 1, and so if the basis were orthonormal, the ith coefficient is simply u dotted with the ith basis vector. So it's even simpler when the basis is orthonormal. And you may look at this and ask two questions. Where have we seen an orthonormal or orthogonal basis before? Think of your basis for R2. The standard basis, the vector 1, 0, 0, 1, both vectors are orthogonal to each other and they both have length 1. Think of the standard basis for R3, 1, 0, 0, 0, 1, 0, 0, 0, 1. Once again, it is an orthonormal basis. Every vector is orthogonal to each other and they all have length 1. So it's not a coincidence that we use the standard basis for Rn, because whenever you have an orthogonal or an orthonormal basis, it makes your life a lot easier. There's one last question though. If you have an orthogonal basis for your space, everything is easier. No need to solve a linear system to express a vector as a combination of the basis vectors. You can simply use this formula with the dot product. So if you have a space of vectors, the question is now, the orthogonal basis will not always fall from the sky. You'll find a basis first which will not be orthogonal. And the question is, if we have a basis that is not orthogonal, is there a systematic way to construct from the given basis one that is orthogonal? And the answer is yes. This will be the topic of our next video, and this will be called the Gram-Schmidt algorithm.